Balancing chemical reactions is very important in combustion technology. Hi, my name is Tom Condra and I'm Associate Professor at the Department of Energy Technology, Aalborg University, Denmark. And today I'm going to show you how to balance a reaction involving methane and atmospheric air under stoichiometric conditions. So what I'm going to do now is I'm going to draw a box up here. And in this box we have what we call the reactants. The reactants are what we're going to mix up before we combust. So we have combustion, and then we end up again with another box, and this contains our products. So we start off again with our reactants, we combust, and then we end up with some products. Now this process here will, under practical circumstances, take perhaps about 1,000th of a second. Good. So let's figure out what are our reactants. So the reactants are CH4, that's the chemical formula for methane. So we'll write methane down here. Now methane is a molecule with 1 carbon and 4 hydrogens. On the other reactants, that is air. Now air, as we know, consists of 21% of oxygen and 79% of N2. Now, we can actually write the composition of air as in terms of what we would call moles or kilomoles. So we put 1 O2. So every 1 kilomole of O2, we have almost 4 times as many N2 molecules. So this becomes plus 3.76 times N2. Now if we go back and we take the 1 plus 3.76 and 1 over 4.76, that will give us 0.21. That's 21% oxygen. Good. So our reactants are, again, methane and air, oxygen and nitrogen. Now the products, under what we call stoichiometric conditions, the products are just simply CO2 and water and nitrogen. Good. So we have CO2, water and nitrogen. So what we're going to do now is we're going to write the equation which will tell us about the relationship between our reactants and our products. So what we do is we write CH4 plus air, that is equal to, sometimes we write an arrow that shows that the process goes in this direction, but it's the equals which is very important. We have CO2 plus H2O plus N2. Now, what we're going to have to do is we're going to have to put some coefficients here. So the easiest way, normally with combustion equations, is just simply putting the fuel as just simply having one kilomole or mole, or what we'd like to work with is kilomoles. The units of these are a kilomole or mole or a kilomole are just simply means the amount, if you like, of a chemical substance. Now we know that air has this composition given up here, so we write outside of that another coefficient, Ns, and we have O2, 1 times O2 plus 3.76 times N2. Now the NS, that is the coefficient, that's just simply a number. The S says something that it is under it says that it's under stoichiometric conditions. A stoichiometric condition simply means that we only have CO2, H2O and N2 as products. So that should be equal to N1 times CO2 plus N2 times H2O plus N3 times N2. And then again, these are coefficients, they just turn out to be simply numbers. And this is what we're going to try to do, is we're going to try and find out the values of NS, N1, N2 and N3. So what we're going to use to find these balances, to find these coefficients, is we use the law of mass conservation. Which simply says that mass is not generated or doesn't disappear. So it simply means that we can write that M reactants is equal to M products. That's simply all. So in other words, we start out with a certain number of kilos here, and then we will end up with exactly the number of kilos over here in the products. Now, as a direct relationship to this, we have what I call the atomic conservation. I put it like this one here, conservation. And this simply means that if I have an atom in the reactants, like a carbon atom, it simply means I should be able to find that the same number of carbon atoms on the other side in the products. And as we can see here, there's one carbon atom here and one carbon atom over here, so it gives us already some information. Similarly, if I have some oxygen on this side, so many kilomoles of oxygen, or so many atoms of oxygen on this side, I should be able to find them the same number of atoms of oxygen on the other side. So this is simply, this is exactly the consequences of what I call atomic conservation. So let's have a look. So then we write 1 times CH4 plus NS O2 plus 3.76 times N2. This goes on to N1 CO2 plus N2H2O plus N3 N2. So what we simply do is we make a balance of atoms between the left hand side and the right hand side. So we start off by making what we call a carbon balance. So carbon balance simply means, as I said, that the number of carbon atoms here should be the same as the number of carbon atoms here. So let's start off. So we have a look on the right hand side. So we have N1 and just one carbon there. No more carbons here. We check over here and we've got one carbon over here. So that's easy enough. So N1 is simply equal to 1. So then what we do is we do a hydrogen balance. So let's again look on the right hand side, and we have H2 here, so this becomes 2 times N2, and then we look on the left hand side and we have 4 hydrogens over here. That's equal to 4. So that simply means that N2 is equal to 2. Now what we do is we do the same thing for oxygen. So we have N1 and we have 2 oxygen atoms here. So we do 2 times N1. We have 1 oxygen atom here, so that becomes N2. And then we look on the left hand side, and we have 2 times is equal to 2 times Ns. 2 oxygens multiplied by Ns, our coefficient which is there. So we already know the value of N1 and N2, so that becomes 2 times 1 plus 2 is equal to 2 times Ns. And we can easily see that Ns is equal to 2. Okay, so now the only one we need now is the balance of nitrogen. So we do N balance. So we'll look over here. There are 2 times N3. So 2 times N3 is equal to is equal to 2 times is equal to Ns by 3.76 by 2. So we already know the value of Ns, so that becomes 2 times N3 is equal to 2 by 3.76 by 2, and we can see that N3 is equal to 7.52. So we have balanced the combustion equation. So the end result looks like this: 1 times CH4 plus 2 times O2 plus 3.76 times N2. That is equal to 1 times CO2 plus 2 times H2O plus 7.52 times N2. So that's our equation. We have all the coefficients. So it might be really nice to check for mass conservation. So we check now that the mass that we had on the left hand side is the same as the mass that we have on the right hand side. So let's take the left hand side. So we have 1 times, and carbon has a molecular mass of 12. Hydrogen has a molecular mass of 1 approximately, plus 4 times 1. And then we have 2 oxygens. 2 times oxygen has a molecular mass of 16, so it becomes 2 times 16. And then 3.76 times N2, and that becomes 2 nitrogen, and nitrogen has a molecular mass of 14. Now that is 14 kilograms per kilomole, so that's 14. If you do the sums now, you will get a value of 290.56 kilograms. Good. So that's the left hand side. Let's do the right hand side. So the right hand side, that becomes 1 times bracket carbon, that is 12, plus 2 times oxygen, which is 16, plus 2 times H2, that is 2 times 1, plus an oxygen there, and that is 16. And then we do finally 7.52 times, and that is 2 times the molecular mass of nitrogen, which is 14. And if you do the sums in that one, not surprisingly, you get 290.56 kilograms. So we can see now that we have both atomic conservation fulfilled up here, and this is the same as mass conservation. So this concludes now the demonstration of the stoichiometric combustion of methane with atmospheric air. I hope you've learned something from this short video. If you'd like to see other educational examples, then you're more than welcome to follow my YouTube channel. Thank you very much for your attention,